Hello everybody. In this video, we're moving on to continuous functions. So continuous functions are going to deal with this problem with limits where you're taking the limit as x goes to a, but you're not really allowed to let x equal a. But when the function is continuous, then we can, which is going to be great. All right, so this video is going to be devoted towards the definition as well as several examples. Maybe we'll have some pictures and a little bit of commentary. And then in the next video, we'll start doing some properties of continuous functions. So let's begin with a definition. So we're going to have a function f with domain D. So this will be a real valued function as usual. And a is going to be actually some element of D. So with our functional limits, a was always some limit point of D, but here continuity is only going to be defined for points in the domain of the function. So we're going to say that f is continuous. Continuous at a. And so here, let's first do it with the coin language, and then we'll shift to the epsilon delta jargon. All right, so if every f of a coin, all right, so it's probably helpful to have a picture here at the start. So we have our function, f going from D to R, and there's some point A in the domain, and then over here you have f of a. So it starts with every f of a coin. So it means I get to put some coin here. So maybe some f of a plus epsilon and an f of a minus epsilon. Okay, so I'm looking at this f of a coin. And I want, for continuity, that every f of a coin contains the f image. Okay, this sounds just like a limit of the intersection of D with an A coin. So I come over here and I find some coin around A. This could be maybe A minus delta, A plus delta, and of course this delta depends on epsilon. And I want that, well, I'm only going to look at points in this A coin that are in D, which in this picture looks like all of them, but in general doesn't have to be. All right, but I only want to look at these points, and I want that all of them get mapped into this f of a coin of radius epsilon. Okay, that's the goal, right? And so what this is telling me is that if I get points that are close to A, then those points are going to get close to f of a. So continuity, in a sense, preserves closeness. Okay, all right. Let's write this down using our epsilon delta jargon. So alternatively, okay, so we want to translate this f of a coin. So for all epsilon greater than 0, so that's our f of a coin radius, there exists some delta, okay, which depends on the epsilon, but we'll usually drop the of epsilon, once we've made this choice. But it's good to remember that it's there, such that if you have, I said A, but this of course should be X. If I have some point in D, and that point is within delta of A, so that means it's within an A coin. Okay, so this delta, right, that's our A coin radius. Okay, so if you have some point in D and it's within delta of A, then f of x and f of a are within epsilon of each other. Okay, meaning that f of x lies in this f of a coin of radius epsilon. All right, so there's our definition in both words and in symbolic jargon. Okay, let's draw another picture. All right, so this verticality picture, right, we've been using this for our limits. What if we move back into the perpendicular axis formulation. So here I have an XY plane, and maybe I have some graph, and I'm looking at some point A, and I want to know whether or not the function is continuous at A. So first, A should be in the domain. So if there's a big hole right here, if I had something like that, then no, it's not in the domain. F is not continuous there. Okay, so it actually does have to have some value at A, right? This is our function F. Okay, so I can look at what that value is. There it is on the y-axis. There's our F of A. And the idea is somebody, of course, comes around and puts a coin around F of A. So there we go. We get a nice coin. There's F of A plus epsilon, and then down here is F of A minus epsilon. Okay, so what I can do is now I'm going to extend some little red lines here. Okay, and what I want to do is to find a coin that, if I draw that A coin, the graph doesn't leave these red bands. So, for example, if I chose my A coin to be like this, okay, so this was my A plus delta, this was my A minus delta, and I say, okay, well, does the graph, if I'm between those points, does it ever leave the band? And the answer is, well, yeah. I mean, look at this. All this stuff here and all this stuff after there, all right, that is all outside. Well, I don't need to worry about past the blue line. That is all outside the red bands. Okay, so here I would have an A coin that was just too big. All right, it doesn't prove continuity because, look, I can have things that are, quote, close to A, namely inside this A coin, but the outputs are not close to F of A because they're not within epsilon of F of A. All right, so but all this means right now is that I chose a poor delta. So what if I chose a better delta? Okay, so let's run these choices back. All right, so it won't let me run any further back, so we'll erase manually. All right, so I run the choices back, and I say, well, what if I chose my coin to be a lot smaller, right? So I'll just do this blue bit. Well, now, when I run these little vertical lines right through the edge of the coin, I see that all of the points, right, lying between these blue lines, right, the values of those functions really do lie between the two red lines. So if I can get this close to A, then the outputs really will be close to F of A. Okay? So the focus here then ultimately is on being able to draw this rectangle where the graph stays inside the rectangle. Okay. In the first case, if we'd have drawn that rectangle, right, you would have had parts of the graph which were leaving the rectangle, and that's not allowed. Okay. So the idea ultimately is somebody gives you the height of a rectangle. You have to give them the base of a rectangle, where that base is centered at A. And the rectangle has to completely contain the graph, right? The graph cannot jump out the top or the bottom, right? Over, within that rectangle. Okay. Now, an important point, which we're going to come back to later when we discuss uniform continuity, is that this rectangle I draw absolutely is depending on the choice of A. That is, if I chose a different input point, like maybe I had a B, okay, so I have some B over here, and somebody says, okay, well, what's F of B? Well, okay, F of B is some point up there. There's my F of B. And if I drew these red dotted lines, okay, around F of B, well, maybe it's going to look something like this now. And I say, okay, I need to stay within here. So how big, right, how wide do I need to make my rectangle, right, or how narrow, if you like, so that everything stays inside? And so you might say, well, okay, I can make it, let's see. I certainly don't want it to, I mean, this is okay over here. I don't want it to go past there, though, right? Because then it would leave. So then I could come on this side and yeah, okay, so I could make a much wider rectangle, right? So for B, I can use a wider rectangle, right? But if I'd started with this rectangle for B and then said, okay, I think that works for A, the answer would be no, it doesn't work for A. So even though we're at the moment writing these deltas as depending on epsilon, in fact, they actually depend on A as well, right? So we're not going to dwell on this too much right now, but again, when we get back to uniform continuity, we'll realize we actually should be writing that the delta depends not only on the epsilon, but on this point A that we're talking about. Okay. Now, one thing we should add to this definition is, of course, this is continuity at a point, but you've probably heard people talk about a function being continuous on the domain. So that's simply going to be described as saying if it's continuous at every point in the domain. So if f is continuous for all A and D, then f is continuous on D. Okay, and this again we'll get back to why we actually care about this delta depending not only on epsilon but on the point that we choose. Is if we want something to be continuous across an entire domain, we can't just pick one delta for every point, right? We're going to have to actually choose a different delta at each point, at least potentially. All right, let's do some examples. So our first example is the constant function, right? What a silly example, right? So let f of x equal c, where c is some real number. Okay, so this is just for any input, we just get the constant function out. And from a pictorial point of view, this should be pretty obvious because if I draw a graph, there we go. So there's f of x equals c. Okay, so there's height c, and I choose any point A, right? Any real number A. And somebody says, okay, I want to pick some c coin. So here we have c plus epsilon, and here we have c minus epsilon. And I want to put some sort of coin around A so that all of the outputs are going to be in in the box, right? So I say, okay, well, I just pick anything, right? So how about I do A plus 1 and A minus 1? And I come up here, and I get this box. And sure enough, the function does not leave the box. Why? Because this is a constant function. It's not going up or down, and the bounds go above and below C. All right? So pictorially, this is really obvious. If we want to write this thing down precisely, right, what do we say? So let's let A be some real number. If epsilon is greater than 0, well, then we know if x and a are within 1 of each other, okay, that's what I was doing down here in the picture, then the difference between f of x and f of a is going to equal, well, f of x is c, and f of a is c. And so that difference is exactly 0, which is definitely less than any epsilon that anybody could give us. Okay? Now you'll notice we never actually used this condition here, that x minus a is less than delta, right? This is supposed to be our delta of epsilon, comma a even if you like, but it doesn't even matter, right? We never even used this condition, and that's because we had a constant function. Okay, so this was true for any a, so this implies f of x equals c is continuous on all real numbers. All right, let's do another example. How about we do the identity function? Okay, so f of x is going to be equal the identity function on the real numbers. All right, so this is just x, right? I put in x, I get out x. All right, if we do this pictorially, it's not as immediately obvious, as with the constant function, but it's also not going to be terrible. So there is our line, y equals x. And if I choose some point, let's say I have my a here, I come on up, and I actually know, because this is the identity function, then the output is also a. All right, so now somebody comes around and gives me my epsilon. So there's a plus epsilon, and here's a minus epsilon. I can draw my bands. And I want to now draw my coin around A so that, oh, I don't like the way this is. It's a little too low or high. Okay. I need to draw my bands so that I don't leave the box. And you can see roughly how I would do that. I just say, oh, well, how about I only go out so far, right, that the function doesn't leave the box. Okay, and it doesn't look perfect here. I really want A in the middle. I'll just try to slide that over just a tad. And you just kind of have to imagine that I drew this perfectly. Okay, so now I get this box. And the function does not leave the box. Okay, well, how wide was this? Well, since this is the line y equals x, then if this output over here is a plus epsilon, then this input down here better be a plus epsilon. And similarly, since this output was a minus epsilon, this could be a minus epsilon. So in this case, I should be using, it looks like, a delta equal to epsilon. All right, so let's write this down precisely. So if a is some real number, and epsilon is greater than 0, then if x is in, well, it's a real number, nothing to say there, but if x and a are within epsilon of each other, then the difference between f of x and f of a equals, well, let's see, f of x is just x, and f of a is just a. And x minus a was assumed to be less than epsilon. And there we go. As long as we choose our a coin to be the a coin of radius epsilon, then our f of a coin is going to contain the image of that a coin. All right, so this tells us that f of x equals x is continuous at any a, right? We chose a arbitrarily, so this is continuous on the set of all real numbers. All right, so it turns out actually that by just doing these two rather straightforward examples, the constant function and the identity function, using an algebraic continuity theorem that we'll get in next video, we can actually show that every polynomial is continuous, right? And in fact, even every rational function, which is a polynomial divided by a polynomial, is continuous, at least on its domain. So that's pretty good. All right, well, why don't we do a non-example? Okay, so everything has been about where continuity does happen. So an easy non-example is, let's write down g of x equals x squared minus 4 over x minus 2. So this function, we saw when we were working with limits, has a limit as x approaches 2. So recall that the limit as x approaches 2 of g of x was equal to 4. Okay, we played this game where we factored the x squared minus 4, canceled an x minus 2, we ended up with x plus 2, and that went to 4. However, 2 is not in the domain. 2 is not in the domain of g. All right, there's a limit at 2, but it is not in the domain, and therefore g is not continuous at 2. Okay, it's just not even a question we're going to ask in that case. Okay, so what about an example where it is in the domain, but you don't have continuity? Well, if it's in the domain, you don't have continuity, easy examples, right, are going to be where the limit doesn't exist. Okay, so let's write down another non-example. So let's take h of x to be this step function, which is equal to either 3 or 1. 3 when x is smaller than 7, and then 1 when x is greater than 7. So pictorially, our h of x, you say, okay, well, before you get to 7, it's up here at 3. But then once you get to 7, it's going to drop down to 1. And we've already seen that the limit as x approaches 7 of h of x does not exist. And so this is actually going to imply, and it's not immediately obvious, but this is going to imply that h is not continuous at 7. All right, well, I say it's not obvious, but let's go back to the definition. The definition of continuity said that, let's actually get all the way up here, every f of a coin needs to contain the f image of the intersection of d with an a coin. Okay, this looks actually a lot like our functional limit definition. So if we head back to our functional limit definition, it said that the a limit equals L if every L coin, okay, that would be f of a in our case, contains the f image, same thing, of the intersection of D, same thing. Intersection of D and a punctured a coin. With continuity, we don't say anything about a punctured a coin. We say it actually has to contain the image of the entire a coin. So if the limit doesn't exist, then you can't even get an f of a coin to contain the f image of the intersection of D with a punctured a coin. Well, if you can't get a punctured a coin, how are you going to get an a coin? So continuity is stronger than a limit existing at a point. So if the limit does not exist at a point, then you're not going to get continuity. Now, what if we look at this pictorially? Well, I'm claiming, right, that I need to be able to get some h of 7 coin. Now, h of 7 is 3, so I need to draw a coin here. So I get 3 plus epsilon, 3 minus epsilon, and we can draw our little lines. And now I need to be able to put some 7 coin down, which is going to contain the function completely. Now, to the left, I have no problem, right? I could make this anything I like. And when I draw this vertical line, hey, look, on the left side of the box, I contain the function. The problem is no matter where I put it to the left of 7, when I put it the same thing on the right of 7, I'm going to be getting the function down here, right, at 1, which is going to be outside the box if, say, I don't know, let's say we made epsilon equal to 1. And now no matter how big or small I try to make this 7 coin, I'm going to be containing parts of the function that are outside the box. Right? I can't get this function inside the box, so I don't have continuity. Okay, if we want to write it down using the precise language, we could say, well, if x is greater than 7, then what is the distance between h of x and h of 7? Well, when x is greater than 7, then I know that the value of h of x is going to be 1. And h of 7 is equal to 3. This difference is negative 2. You take the absolute values, and this is 2. So this tells me that for all x greater than 7, the difference between h of x and h of 7 is equal to 2. And that will certainly be greater than many epsilons, right? It's certainly greater than, say, 1. Okay, so that would be, say, some potential epsilon. Okay, so that means that no matter what coin we choose, we can never get this difference, right, to be less than, say, epsilon equals 1. Okay, so all of these reasons, they tell us h is not continuous. at 7. All right, one more example. This gets back to our discussion of monster functions. So here we're going to let's go back to f, say, this is going to be, well, we looked already at sine of 1 over x. And when we graph sine of 1 over x, we saw that it just looked absolutely crazy near 0. And in fact, we were able to show that the limit doesn't even exist at 0. Okay, if the limit doesn't exist at 0, then we certainly have no hope of continuity there. And in fact, it's not even defined at 0, so like there's just no discussion of continuity at 0 for this function. But what if we do the following? I'm going to stick an x in here, and then I say, well, I still know it's not defined at 0. But what if at 0, I make the value of this function equal to 0? Okay. So what I claim is that, well, first, obviously 0 is now in the domain of the function, but even better, I claim now that f will be continuous at 0. So that's the claim. F is continuous at 0. All right. Well, how are we going to see that? So here's what we'll do. We need to show that for any epsilon, right, that's going to give us a 0 coin, that I can put a coin around 0, that's going to be my input, which is going to get mapped by f into that 0 coin of radius epsilon. So let's let epsilon be positive. And let's now take a look at the difference between, well, just some arbitrary f of x and f of 0. I don't know, right, immediately what I want my x to be, right? I know it needs to be close to 0, but how close? Right? Well, let's use this to figure it out. So let's see. I know that f of x is going to equal x times sine of 1 over x, right? Or, well, possibly 0, right? So let's look. Actually, there's two cases. So we have x sine of 1 over x minus, well, f of 0 is 0, so just 0 there. So this is when x does not equal 0. And when x does equal 0, well, I get f of x minus f of 0 is f of 0 minus f of 0. It's just 0. All right, so in the case where x is equal to 0, I get 0, which is definitely going to be less than epsilon, right? So in this case, I'm definitely less than epsilon. But what about this case? So this is just going to be the absolute value of x times the absolute value of sine of 1 over x. All right, well, let's examine that function a bit. Well, what do we know about the sine function? We know that the sine function always lies between -1 and 1. And so if I take the absolute value of the sine function, then this is always going to lie between 0 and 1. Right? Absolute value gets rid of all the negatives, makes them all positive. So this tells me that this absolute value is less than or equal to 1. And therefore, the absolute value of x times this absolute value of sine will be less than or equal to the absolute value of x times 1, which is, of course, just the absolute value of x. But let me rewrite it slightly as the absolute value of x minus 0. Now, this is the thing we're allowed to control, right? In all of this discussion of continuity, we are given an f of a coin, and we have to find an a coin, right? That is, we need to find a delta such that x minus a has absolute value less than delta, or x and a are within delta of each other. So down here, right, this is the thing I actually get to control. How far apart is x from 0, right? Because I'm trying to show continuity at 0. Now, f of x minus f of 0, we know is equal to the absolute value of x times the absolute value of sine of 1 over x when x isn't 0, which is less than or equal to the absolute value of x minus 0. And at the end, I want this to be less than epsilon. So why don't I just do that? This tells me now if the absolute value of x minus 0, that is, the distance between x and 0, is less than epsilon, then the distance between f of x and f of 0 is also going to be less than epsilon. Again, remembering that in one of those cases where x is 0, we actually get 0, which is certainly less than epsilon. All right, and so this here implies that f is continuous at 0. Okay, so it takes a little bit of manipulating here, right? In your mind, you figure, okay, what does I need to show? I need to show that the difference between the output of the function and the output at the point I'm talking about is less than epsilon. And if I can rewrite everything so that I end up back at absolute value of x minus, well, whatever the point you're checking at is, if I can get it in terms of that, well, that's the one thing I can control. Okay, and so I'd say, okay, what do I need to make that absolute value so that the original one is now less than epsilon? Okay, and so this is the punchline. Okay, so we've now actually shown that this monster function is actually continuous at 0. All right, so in the next video, we're going to go into some properties of continuity, and I'll use those properties to really expand what kind of functions we know are continuous. All right, we will see you next time.